Today, we're talking about a revolution in how we find new medicines. It's not just about clever chemistry, it's about speed. It's about a radical new way of thinking that creates a shortcut to discovering life saving drugs.
I mean, think about the scale of the problem. There's a practically infinite number of molecules that could possibly exist. Trying to find the one that fights a specific disease, that's like searching for a single, unique grain of sand on every beach on Earth. It's slow, it's incredibly expensive, and honestly, a lot of it comes down to luck. But what if you could just flip that whole idea on its head? Instead of searching for a needle in a haystack, what if you could build the perfect needle from scratch? And not just one, but thousands of different versions of it to test all at once. That's the huge shift we're going to explore, moving from blind searching to intelligent building.
Right, so let's get into the drug discovery challenge. Making and testing potential new drugs has, for the longest time, been a painfully slow process. But a technique called solid phase organic synthesis, or SPOS, is a total game changer. It massively speeds up a crucial step called lead optimization. That's basically taking a promising molecule and tweaking it over and over to make it perfect. You see, the old way, a chemist might spend weeks or even months in a lab just to make one single new molecule to test. And if it didn't work, well, back to the drawing board. The new way we're talking about, called combinatorial chemistry, is completely different. It's about making entire libraries of molecules. We're talking hundreds, even thousands, all at the same time.
So how on earth does that even work? Well, it all comes down to the power of combinations. The idea itself is actually pretty simple, but the results, they're absolutely incredible. Okay, so a combinatorial library is basically a huge set of related molecules made from a few starting pieces. Here's a great analogy. Think of an ice cream shop. Maybe you've only got 2 types of cones, 8 flavors of ice cream, and 4 different toppings. By mixing and matching those in every single possible way, you can create a massive menu of unique treats. Well, chemistry can work exactly the same way. And in the specific study we're looking at today, scientists did just that. They started with 2 core chemical skeletons, they call these scaffolds. Then to each of those, they attached one of 8 different amino acids. And for the final touch, they added one of 4 different chemical modifiers to cap it all off. And here is where you see that power of combination in action. 2 times 8 times 4, that equals 64. With just a handful of building blocks, they created 64 completely new and unique molecules, an entire library of potential drugs, all made in one coordinated shot. Now, what's really fascinating is how they physically pulled this off. The secret sauce, the technology that makes all this possible, is called solid phase organic synthesis. It's the ingenious workbench that lets chemists build this molecular library so efficiently. Probably the easiest way to wrap your head around this is to think of it as chemistry on a leash. See, instead of having your molecules just floating around randomly in a liquid, you physically anchor your starting molecule to a solid object. This gives you incredible control. It makes every step, adding new pieces, washing away junk you don't need, super clean and precise. And what is that solid object? It's a tiny little polymer bead called a resin. You can think of these microscopic beads as individual workbenches. And the amazing part is, you can have millions of these little workbenches in a single tube, all building the exact same molecule at the exact same time. So the very first piece you attach to that resin workbench is called the scaffold. This is your foundation. It's like the chassis of a car that you're about to customize. In the study we're looking at, the scientists started with 2 different chassis designs to build their library from. Then, after all the new pieces have been added and your molecule is fully assembled on the bead, there's one last crucial step: cleavage. This is a special chemical reaction designed to cut that leash, releasing your brand new finished molecule from the resin bead. Only then is it free to be collected and, most importantly, tested. So let's dig into the case study and see how these scientists actually put this molecular assembly line into practice. They used it to build their library of 64 different compounds, a type of molecule they call glycopeptoids. The whole thing was like a perfectly choreographed dance. First, they anchored the scaffold to the resin beads. Then, step by step, layer by layer, the other building blocks were added in a super precise sequence. And finally, once everything was in place, the finished molecules were cleaved off, ready to go. Now here's the kicker.
This wasn't some poor grad student doing this by hand in 64 separate flasks. Nope. This entire 5-step process was done in parallel for all 64 compounds at once, inside a robotic synthesizer. A machine did all the heavy lifting, precisely adding the right ingredients to the right wells, building the entire library at the same time. This is literally the molecule factory in action. Okay, now for the most important part. Building a cool library of molecules is great, but what's the point? Well, the whole point was to test these 64 brand new molecules against a real-world enemy, the filarial parasite. It's a nasty parasitic worm that causes some really devastating diseases. So, the big question is, did it work? After all that clever chemistry and automation, did any of these 64 custom-built molecules actually hit the target? And the answer is a resounding yes. When they tested them against a key enzyme that the parasite absolutely needs to survive, 2 of the molecules really stood out. One of them shut down the enzyme by 57%, and another by 51%. To put it simply, these brand new molecules were successfully gumming up the parasite's internal machinery. That's a huge win. But, what might be even more important than those 2 hits were the clues the entire library gave them. The data started to show patterns. Molecules that had certain features, like halogen atoms or specific amino acids like proline and valine, tended to work better. This is priceless information. It's like a roadmap that tells chemists exactly where to look to design the next round of even better drugs. So let's zoom out and look at the bigger picture. Is the real story here just about those 2 promising molecules? Not even close. The researchers themselves said it best in their paper. They wrote that this technology has reduced the time of lead optimization dramatically. And that's the key. It's a fundamental change in the speed of science. The real breakthrough isn't any single molecule they made. It's the molecule factory itself. It is a powerful, repeatable engine that lets scientists generate and test new ideas at a speed that was just unimaginable before. It turns drug discovery from a slow, painful march into a rapid-fire series of smart experiments. And that really leaves us with an amazing thought to end on. What if the cure for the next big disease isn't something we just stumble upon after decades of searching? What if it's something we can actually build, test, and perfect rapidly and by design? That's the incredible future this kind of technology opens up.